CNBT 1311. Good morning. This is video 1, chapter 12. 12.1. Alright. Notes on materials. Building materials, life cycle assessment, concrete, masonry, steel, non-ferrous metal, stone, wood, lumber. We got a lot to go through, and this is the last chapter of the book, except for the appendix. Appendix in this book has a lot of good information in it for your design future. Keep the book. Don't get rid of it. All right, let's get on with this. All right, excuse me. Building materials. This chapter describes the major types of building materials. That's why we call it building materials. Each material has distinct properties: its strength, elasticity, and stiffness. All right, here's a definition of elasticity. Elasticity, its ability of material to deform under stress, bend, stretch, or compress, and return to its original shape when the applied stress is removed. Now, if you're an engineer, you're going to take a course in stress and strain. It'll be called Strength of Materials, and you'll go through all manner of calculations. Yeah, that was a fun course. I enjoyed that. All right, I did. Still got all my books. Used it a lot while I was engineering. All right, so that's elasticity. Think about a rubber band. It's elastic, right? You stretch it, and you let it go, and it goes back to its original shape. Unless, of course, you overstretch the bloody thing and it goes beyond its elastic limit. And then it goes into what's called plastic deformation. All right, I know y'all are excited about that. Materials that undergo plastic deformation before actually breaking are termed ductile. Okay. In engineering terms, plastic means it's exceeded its elastic limit. You bent it. How's that? So you can take a coat hanger and you can bend it a little bit, let go, and it'll go back to its original shape. You keep bending it some more, and it'll get to a point that it won't return back to its original shape. You have gone out of the elastic limit and into a plastic deformation. Brittle materials is just that. It breaks. It's like a cracker. Okay. I'm going to try to make this as non-engineering as possible for you. All right. On the other hand, have low elastic limits. Well, that makes sense. Go take a piece of uncooked pasta out of the bag, a spaghetti noodle, and try to bend it without breaking it. Okay. All right. So that's brittle material. Glass is brittle. Okay. Because brittle materials have less reserve strength than ductile materials, they are not suitable for structural purposes. All right. Stiffness is a measure of the force required to push or pull a material to its elastic limit. That's the stiffness. How stiff is it? How does it resist being pushed into this elastic zone and then allow it to come back? Okay. Push or pull a material to its elastic limit. A material's stiffness, along with its stiffness of its cross-sectional shape, are important factors when considering the relationship between your span and deflection under loading. This is the deflection of beams and columns and stuff like that. It's the engineering stuff. Okay. But you need to get a good grasp so that you can talk intelligently to your structural engineers. The dimensional stability of a material is just that. How stable is it to maintain its original shape? It responds to temperature and moisture content. The manner in which it's detailed and constructed to join with other materials. The resistance of a material to water and water vapor. The thermal conductivity. Okay. Is it highly expansive? during the cycle of heating and cooling? Does it suck up water like crazy? Um, you take a piece of wood that you bought, lumber, and it's in the crib at Home Depot or Lowe's, and you've looked at it and it's as straight as it can be, blah, blah, blah. You throw it in the back of your pickup truck, you go home, you lay it out in the hot sun, and you come back out at the end of the day because you haven't used it yet, and that sucker's starting to warp, starting to twist, and you're going, what's going on? Well, the relative humidity inside of Lowe's is different than the relative humidity in the heat sitting out in the sunlight in 115 degree temperature down here in the Gulf Coast area. All right. So then if it rains and gets cool, that board might untwist and go back to its original position. I bought some ground contact 2x12s to redo the decking on my trailer before I had my back surgery. And it was as straight and dimensionally stable as it could be when I got it at the lumber yard. I pulled it out of the air conditioning of the lumber yard, got it home, laid it on the trailer to start cutting and coping and beveling the ends before I welded the front and back toe plates on it. And that stuff was twisting like a son of a gun. Because of the moisture content. The waterborne salts that they used to treat that lumber was being sucked out by the hot sun. So I built me a cross jack and pushed that stuff down flat, welded the front toe plate, moved the jack to the back, jacked the boards in place, welded the back toe plate, and here we go. We're not building a piece of furniture. We're putting wood decking on a trailer, but that's dimensional stability. That's a term. A material's transmission, reflection and absorption of visible light and radiant heat. Now, we've talked about this in the HVAC chapter. The density or hardness of a material determines its resistance to wear and abrasion. Well, that makes sense. You got sandstone you're going to use for a countertop as opposed to good polished granite like I put in my kitchen years ago. That sandstone's not going to last as long as, it's not going to be as wear resistant because it's more porous, it's less dense, it's less hard. Okay. The ability of a material to resist combustion, that's fire retardant. I did not mark that out. The ability of a material to resist combustion. What's its fire retardant? You know, what's its fire rating? Okay. And with its standard exposure to fire and heat and smoke and toxic gases. All right. All your plastics, when they burn, they emit a very toxic gas. Some of it's cyanide gas, and that sort of thing. Color, texture, and scale of materials are obvious considerations in how it fits in the environment for people and how it makes them feel and work and produce what they're getting paid to produce. Many building materials are manufactured in standard shapes and sizes, and these stock dimensions, however, may vary slightly from one manufacturer to the next. They should be verified in the planning and design phases of the building so that unnecessary cutting or wasting of material can be minimized during construction. Now, we all know a 2x4 is not 2 inches by 4 inches unless you're ordering special rough cut full dimension lumber. Standard 2x4 is 1.5 inches by 3.5 inches. Now, what about a 2x12? That's 1.5 inches by what? 11.25. So best way to do it is if you're going out And Lowe's and Home Depot and the lumber yards, they all will tell you what the exact dimensions of these things are. They'll tell you what the nominal dimension is, and then they'll tell you what the actual dimension is. So check your dimensions before you start laying out your wall. All right. The evaluation of building materials should extend beyond their function, economic, and aesthetic aspects. We're talking about the embodied energy and of a material. Okay. All right. And the embodied energy includes all the energy expended during the life cycle of a material. And the American Institute of Architects has an environmental resource guide, and there are all kinds of other resource guides out there. You can even go to treehugger.com, the website, treehugger.com, and I am not making that up. That is a real bona fide group of greeny weeny architects. Okay? And I'm not making fun of greeny weenies. Okay? But some of them are just off the rails because of the embodied energy. Okay, the life cycle beyond their function, economic, aesthetic aspects, including assessing the environmental consequences associated with their selection and use. And that goes into the manufacturer. This examination, called a life cycle assessment, it encompasses the extraction and processing of raw materials, the manufacturing, packaging, and transportation of the finished product to the point of use. Everything from the raw material all the way to the point of your job site. And maintaining the material in use after you get it built. Is it a high maintenance material? Do I have to paint this thing every 5 years? Do I have to reseal it every so often? And what about the possible recycling and reuse of the material after the structure has ended its life? What if we're going to tear that structure down in 25 years and put something else up? Can we recycle that material? All right. What's the cost of the disposal, et cetera, et cetera? And this assessment process consists of 3 components. This assessment process consists of 3 components. This is called a life cycle assessment. The life cycle assessment, okay, consists of 3 components: the input, the life cycle inventory, and the output. Now, this all sounds weird, but it's not. Let's go up here and I'll give you some examples of what we're talking about. All right. The Tesla Model 3, just one Tesla Model 3, holds an 80 kilowatt lithium ion battery. The CO2 emissions for manufacturing that one battery ranges from 2.5 metric tons to 16 metric tons. And Tesla finally released the true data on its supply chain emissions for 2022, which is equivalent to roughly 30.7 million tons of carbon dioxide. That's a huge change from what the company reported last year. Of course, nobody wants to tell you exactly how much bad gas they're putting out. Where's the electric car, dude? This is supposed to be like to save the world, all right? Like that misguided little Swedish girl that runs around screaming about stuff while she lives on a super duper expensive sailboat with her daddy, and that sailboat's made out of fiberglass and all kinds of bad stuff for the environment to make. But hey, what can I say? She flies around on private jets to do her talking. And all the carbon dioxide and pollution from that. Oh, goodness me. Anti-him, anti-him. All right. The CO2 emissions, or the CO emissions of the aviation industry, It really should be carbon dioxide, CO2, but hey, what can I say? All right. The emissions of the aviation industry by flight type from the year of 2000 to 2021, the international aviation almost emitted 384.5 metric tons of carbon dioxide worldwide. That's all the commercial flights in 1 year, okay? And during the same year, the CO direct emissions of domestic flights amounted to 327.9 million metric tons. Now, the problem with figures is who's collecting the data and what's the data input analysis, okay? That gives you an idea. Now, I said before that if you take all the jet fuel that it takes to fly, all the commercial flights around the world in 1 year, that's everything around the world. Cargo flights, people flights, all the commercial flights. That amount of fuel is used to only make 250,000 Tesla batteries. Because you've got to use fuel to mine the lithium, okay? Then you got to use fuel to transport the lithium to the lithium plant. Then you got to use fuel to process the lithium, and it's a nasty process. A lot of pollution, pollutants come from that. Then you've got all that waste from the lithium. So, is it truly green? Of all the materials used to make concrete, that cement has the highest EE, environmental efficiency, okay? All right. This is still low compared to like MDF board or glass manufacturer, and very low compared to plastics, rubber, aluminum, steel, and copper. All right. It takes a lot of energy to make aluminum, and rubber, and plastics, and steel. Hot rolled. We're talking about hot rolled steel, and even cold rolled steel studs. That sheet comes out hot. Okay, off the steel mill when they coil it. And copper, the greatest amount of embodied energy. Okay, this is embodied energy in a building can either be from low embodied energy materials such as concrete or high embodied energy materials such as steel. Okay, for most people, it's more useful to think in terms of building components and assemblies rather than individual materials. So, if you're doing the greeny weeny thing, what's the total energy to put up a reinforced structural concrete wall as opposed to a structural steel frame? Now we look at the cost per square foot and the life cycle of that. Cast in place concrete is very plastic. Your structural engineers can do a lot with it as opposed to a structural steel frame. I love structural steel and reinforced concrete, but they have their place and their usage. The cost of form work in concrete is your highest cost. Your forming to get that right, get it engineered right. Second is the reinforcing rebar, and the actual placing of the concrete is at the tail end of that total cost. Wind turbine blades. Let's go talk about greeny weeny wind turbines. Okay, and I'm not anti-wind turbine. All right, I've told you before, solar panels. Oh, and we're not even going to talk about the carbon footprint to make a solar panel. That's just way up there with the freaking Teslas. All right, wind turbine blades are huge. The average rotor diameter in the United States, from a U.S. government report, was 418 feet. That's the diameter of the rotor. All right, so a single blade is almost as big as a Boeing 747's wingspan. They're designed to be resilient against heavy winds and weather conditions. The blades have a lifespan of about 20 years on the high end. They start ultrasonic testing those blades, I remember correctly, somewhere around 10 to 12 years into their life. And they're looking for cracks before they're retired or replaced. Now, these things are made out of fiberglass, which is a thermoset resin. You can't remelt it and grind it up into plastic pellets like you can PVC or high-density polyethylene. You can't recycle it. So what do? Well, most are constructed using composite structure, fiberglass and epoxy, built on top of a balsa wood. Now, where does balsa wood come from? Comes from the forest. We're cutting down trees. Oh, Annie M. All right. But they're wrapped in epoxy, fiberglass epoxy. This is a thermoset. All right. It adds stability and strength and flexibility, but recycling options in this report is said very limited. There is no recycling of a thermoset resin. You can't unthermoset it because it's a chemical set. You can't remelt it. You can't grind it up and put it back through a pelletizer like you can PVC or high-density polyethylene or a lot of your plastics, or most of your plastics. Most wind turbine blades, well, when they're done, they end up in landfills. They chop them up and they bury them, and they're going to be there for thousands and thousands of years. All right. In the U.S. alone, more than 2 million tons of decommissioned blades are projected to be sent to landfills by 2050. Okay. So now how green is that? Well, there is no free ride. There's no such thing as a free ride. You don't get free bubble up and rainbow stew, and that's from a Merle Haggard song. Okay, has nothing to do with alternative lifestyle partying. All right, so don't go run off to HR and say I said something nasty. You look it up. Came from an album and a song on Merle Haggard's album. I had to explain that to some people in the DEI committee I'm on at Lone Star College. They said, "Oh, you said Rainbow Stew." And I'm going, "Yeah, it's a Merle Haggard song." "Oh, well, bud." So I had to go research urban definition of it. And I'm going, oh, my goodness. So, anyway, what can I say? So, if any of y'all got offended about that, I apologize. But it's a Merle Haggard song before it was anything else. So, and it had nothing to do with that. It had to do with the utopian mindset. All right, enough of that silliness. All right, we talked about elasticity, plastic deformation, brittle stiffness, span deflection under loading, dimensional stability, and thermal conductivity. And you're probably running for the door right now going, "Oh, stop it, stop it." Okay, so let's get back to life cycle and carbon footprint. I did a lot of research when I was a student at A&M for a engineering professor. We were doing a carbon footprint analysis of solar panels, aluminum, building materials, all kinds of stuff. We were doing this back in the early 70s, long before the Greeny Weenies got involved. The Greeny Weenies have been around a long time. I used to subscribe to Mother Earth News. They had all kinds of alternative building stuff in there, alternative energy stuff. They even had an article that spanned, I think, 2 issues of a guy that took an old Opel car. He was an aviation mechanic, and he stuck a jet turbine starter motor in it, hooked it up to the transmission, and put a Briggs & Stratton gasoline-powered engine in it, drove a generator, and had a bank of batteries in the trunk, and he made him a hybrid car. Now let's go back to EVs. An EV, electric vehicle, as long as you're in an urban environment and you're doing short trips like delivery and that kind of stuff, or just going to work and back, and you've got a guaranteed recharging station at the end of both trips, that ain't a problem. That's probably a very good, a very, very good use for that. But you try to travel from Houston to El Paso, Texas. That's a 12 to 14 hour run um, in an EV, and expect to get that thing charged. I can pull into any station and in 20 minutes have my gas tank filled up on my Tundra hybrid. Now Toyota knew this early on. Toyota's been making hybrids for years, many, 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 many years, and they knew from a good engineering standpoint that the best of both worlds was a hybrid. Low speed, you use the electric, and then you've got charging devices on the deceleration of the car that charges that, but you've got a gas engine that works, and the electric motor and the gas motor are in a line, and that's the smart way of balancing this out. Okay, you're not putting all your eggs in one basket. All right, he has a chart over here, the embodied energy in building materials. A BTU, you know what the BTU is. What is a BTU? It's a British thermal unit, remember? And what's 1 ton of refrigeration? It's 12,000 BTUs, right? All right. Sand and gravel is 18, wood is 185, lightweight concrete is this, gypsum board is that. Now you can read down through here. Now, what does this mean to us? Not really much. If I need a reinforced concrete foundation wall, I'm going to use reinforced concrete. And yes, this is the embedded energy, the E of the concrete. So let's go back over here to this life cycle assessment thing. We got inputs, life cycle inventory, and outputs. Inputs are your raw materials, the energy to harvest the raw materials and process the raw materials, and water. Now, this is water in, and you got water coming out, wastewater. And what are you going to do with the runoff? The leachate off of lithium mining, okay? You just can't let that run into the stream. Well, they do in China, but okay. Speaking of lithium, Afghanistan is the Saudi Arabia of lithium. It hadn't even been mined yet. That's why China wants Afghanistan. That's why they built that super highway going in from the corner of China into Afghanistan. They want to go in there and start mining that lithium for the batteries. All right. So you got acquisition of raw materials, and it talks down here the impacts. The material renewable, is it renewable or non-renewable? If it's a thermoset resin, you can't recycle it. If it's plastic like PVC or HDPE, yeah, it can be ground up and then repelletized and then reused, recycled. That takes energy. All right. Non-renewable resources include metals and other minerals. All right. Well, you can recycle metal. You can grind it up. Aluminum. There's a big aluminum recycling plant over off 290 where they collect scrap aluminum, melt it down into ingots, and send it off back to the aluminum extruders. Same with steel. A lot of your steel today is recycled steel, ground up, crushed up cars, and they resmelt it. Renewable resources such as timber. And what do we mean by renewable? That means when you cut a tree down, they plant new trees, and then in 15 to 20 years, with proper management of the tree form, that timber's ready to be reharvested. And they vary in their rate of renewal and their rate of harvest. and the rate of harvest should not exceed their rate of growth. Well, that makes sense. You don't want to cut down a freaking tree in your tree farm until it reaches its maturity. Um, how much energy and water is required to process the manufacture of the and package and delivery? All right, well, delivery comes over here. So after we get the product made, then we have transportation. Is this material or product available regionally? We talked about this early on. You know, you might find some super Captain Billy Whiz-Bang material that's way up in Canada, and you want to use it on your project in Houston. Well, you've got to get that, number one, from Canada down to Houston. So is there something local, and we talked about this before, that's more economical? You don't have to pay all that transportation cost. Uh, is your construction crews, your skilled labor in this region, are they able to use Captain Billy Whiz-Bang material? Um, do you have the skilled labor to construct it? All right. If you ever watch those wind turbine blade trucks, take them wind turbines out to Sweetwater, Texas. Those things are long. Got to have special trucking. It's oversized loads. They can't just turn a sharp corner. Um, all that cost. Construction use and maintenance. Does the material perform its intended function efficiently and effectively? How does the material affect the indoor air quality and energy consumption of a building? Now we're talking about outgassing. We talked about that when we're gluing in carpet, like in a commercial building. Um, as that adhesive in that new carpet outgasses its smell, the new smell. What is that smell? Is it radon? Is it some VOC, volatile organic compound, that's going to make people get sick? Are we going to have to ventilate that space for a week until all that outgassing slows down? All right. That's why plastics, um, um, some of them have a UV inhibitor in them, some of them don't. They're always outgassing. That's why vinyl siding gets brittle um, over its life cycle. How durable is the material or product, and how much maintenance is required for its upkeep? If I want a really nice New England shiplap wood home down here in this petri dish of bacteria in Gulf Coast, I'm going to have to paint the thing, and so it doesn't rot. Is there a better product? Maybe I should use hardy siding. It's a fiber cement siding. I've mentioned hardy before. I like hardy siding, but it needs to be put over wall sheathing, over your studs, um, so that you're not asking that brittle concrete panel to span the stud distance. Give it a uniform base. And then it's not going to rot. That hardy plank will, or hardy siding will not rot. And you can use just about any kind of paint on it. And what's the material's useful life? How long? What's the lifespan of that material? Okay. Now your manufacturers are all going to stretch these claims for useful life. All right. A lot of people got sold cheap vinyl siding to go over their house. Don't ever have to paint it again. Yeah, in about 15 years down here, in this heat and sun, that vinyl siding started getting brittle and start cracking because it's outgassing. Um, usable products, disposal, recycling, and reuse. These are all areas you got to worry about. All right, how much waste and how many toxic byproducts result from the manufacture and use of the material or product? All right, outputs. Okay, outputs, waterborne effluents, atmospheric emissions, solid waste, other environmental releases. Okay. Um, Remember me talking about asbestos siding? It was a cement asbestos, and then you had asbestos floor tile. Best thing to do is cover it. Don't remove it, because then you're going to have asbestos remediation, and all kinds of people are going to get involved in this, and you may not even get a permit to dispose of it. So the best thing to do is cover it. Um, I know a contractor up on Lake Belton not too long ago needed to re-side or put new siding on a house. And he got there and he found out this was some cement asbestos siding. And they were like, oh God, what are we going to do now? So they put furring strips over that siding in alignment with the studs behind it, and then covered it with hardy plank. They encapsulated it so they didn't have to dispose of it. When I did my kitchen floor, I had a feeling that that old tile in the kitchen, vinyl tile, was asbestos. When my flooring guy got in, he said, yeah, it probably is. So we floated over that, and we roughed that stuff up, floated over it, and then put the new high-tech composite vinyl over that. We encapsulated it. All right. Evaluating the choice of a building material is a complex matter that cannot be reduced to simple formula yielding a precise and valid answer with certainty. There is nothing certain in this. You can't have a mathematical formula that said, yeah, this is the right thing to do. This is a balance, okay? Y'all can read through all of this, okay? You may have a lower energy material on the front end, but in actually installing it and through its life cycle, it may be higher, all right? You might use a higher energy material that will last longer, require less maintenance. All of this has to go into your planning. And this is what separates a professional and a good designer from a chuck in a truck. All right. Reduce, reuse, and recycle best summarize the kinds of strategies that are effective. Reduce building size through more efficient layout and use of spaces. Reduce construction waste. Specify products that use raw materials more efficiently. Substitute plentiful resources for scarce resources. This goes back to the Captain Billy Whizbang thing up in Canada, to what is readily available in Houston, Texas. Reuse building materials from demolished buildings. There are companies that specialize in this. Rehabilitate existing buildings for new uses. This is always fun. This is called remodeling, okay? Rehabilitate existing buildings. You take an old building that was made in, I don't know, let's say the turn of the century. Not this century, the last century. 1898 to the early 1900s, okay? And you're going to turn it into something. There are companies and architectural firms that specialize in that. And it's a fun engineering project. You get hired and go in there, do a structural analysis of the existing structure, and you get to working with the architect, figuring out what the client wants. Yeah, it can be fun, but it's expensive. And I'll give you a word of advice in remodeling. What you think it's going to cost is way lower than the end cost. You get into a remodeling project and a rehabilitating project, and you'll start digging up bodies, not literally bodies, but, well, yeah, sometimes you do. You get down and redo a foundation and find out that building was built over a burial mound or something. Then you got problems. But outside of that, you'll get in there and go, uh-oh, we're going to have to go in here and shore up the foundation. We'll have to call ramjack and screw those giant metal screws down into the earth, and then jack up that section of the foundation, and then have to go in and re-pour the concrete that we jackhammered out, saw cut and jackhammered out. So I think you get the idea that there is not a one-size-fits-all. There's not a magic formula that's going to make this easy peasy. So we spent 40 minutes, and we're just now getting into concrete. Okay. All right. It should be no surprise that concrete's the first material that that he used. Now, concrete has been around. Reinforced concrete has been around for centuries and centuries. Before the Portland cement industry, and just go Google and watch a YouTube video on how they make Portland cement. An actual cement plant takes a lot of heat, and giant balls that crush it all up into the flue furnace and all that good stuff. It's quite impressive. All right, the Romans, the ancient Romans, not the modern Romans, they had concrete, reinforced concrete, and they didn't have Portland cement. They couldn't go to the supply house and buy a bag of Portland cement. They used fly ash. Actually, it's volcanic ash. All right, and which is a pozzolan. That means that it absorbs water and gets hard. Okay. If you've got an outdoor fire pit and you're burning wood and so you can drink your wine or your bourbon with your lover, and in a nice romantic setting, and you don't cover it and it rains, and you want to go scoop out the ash to clean it up, you'll notice that over a period of time that the ash is hard because it's absorbing that water. Now, if you take a bituminous coal, like from a coal-fired power plant, or volcanic ash, that's a super-duper pozzolan. And back in the late 70s and early 80s, we used to substitute a percentage of the cement in the reinforced concrete with the fly ash from the coal-fired power plants. It was so they had all this fly ash left over, and the American Concrete Institute and the Portland Cement Association started doing research. I was on the committee, one of the committees, and it became quite prevalent to not use so much Portland cement and substitute some of that with fly ash. And you would go through your mix calculations as an engineer and figure out what percentage fly ash we can use and how much Portland cement we're saving and what is our ultimate strength. Is it going to affect it? A rotary kiln is how they make that Portland cement. Burning a mixture of clay and limestone, calcium carbonate, in a rotary kiln and pulverizing the resulting clinker into a very fine powder. And that kiln is hot. It uses a lot of heat. Okay. So Portland cement is a hydraulic cement. Okay. All right. And here goes the types. Okay. Type 1. We have a type 1. You can read this. A type 3 and a type 2. All right. Type 1 is used for general, having none of the distinguishing qualities of the other type. Type 2 is a moderate Portland cement. It's used in general where resistance to moderate sulfate action is required, where heat buildup can be damaging because the stuff does get hot when it's hydrating. It's an exothermic reaction. It gives off heat. All right. And type 3 is a higher early strength, Sometimes for highway repair, they use a higher early strength Portland cement. And this is all in the mix designed by the structural engineer. Um, so if you're gang structuring a high-rise building out of cast-in-place concrete, you might want to spend the extra money for higher early strength. That way, you're not having to wait for the previous floor to reach its strength. All right, it's 28-day strength, so you can start adding more floors to it. All right, there's two. We'll get into that in a little bit, but you have a 7-day strength and a 28-day strength. Um, and core samples are taken at the site of the pour, and some of the core samples, they're just round cylinders of concrete. They're saved for the 7-day break, and then they're saved for a 28-day break. And the testing lab takes them back, puts them in a steam room, lets it cure, and they'll do a 7-day break and give you a report, and then they'll do a 28-day break and give you a report. All right. And type 4 is low heat. It generates less heat of hydration. And the type 5 is a sulfate-resisting Portland cement. It's used for resistance to severe sulfate action is required. All right. Now, remember me telling you about the reinforced concrete sewer pipes and how the sewer gas, which is hydrogen sulfide, would rise up to the top of the pipe and mix with the condensated water and turn into sulfuric acid and eat away at the cement, the calcium carbonate, and destroy it. And then the aggregate was exposed, and then the rebar gets rusted, and the top of the pipe falls in, and bad things happen. People's backyards sink. All right. Air and training Portland cement. It's a type 1, type 2, or type 3 to which a small quantity of air and training agent has been underground during a manufacture. It is designated by the suffix A. When you go, next time you're at Lowe's or Home Depot, go to where they're selling bags of Portland cement and look at all the different kind of cements they got. And see if you can't pick these designations out. And we're not even talking about non-shrink grout, high strength non-shrink grout. So, reinforced concrete. It's cement, it's water, and it's aggregate. The aggregate is fine aggregate, which would be like sand, and it's coarse aggregate. Okay? All right. Now, the water used in a concrete mix must be free of organic material, clay, and salts. It's got to be good, clean water. And you can't use seawater. You can't use salt water. A general criterion is the water should be fit for drinking. It's got to be potable water. Cement paste is a mixture of cement and water for coating, setting, and binding. We already talked about that with bricks. The aggregate gives you because the aggregate represents from about 60% to 80% of the concrete volume, its properties are important. At one time, limestone, because regular hard aggregate was hard to get, so American Concrete Institute and the Portland Cement Association, they did research on can we use limestone aggregate, and there's a whole code for that. You got to watch the quality of your fine aggregate or your sand. He defines it with a particle size less than a quarter inch. There's coarse aggregate, and the maximum size of coarse aggregate in reinforced concrete is limited by the size of the section and the spacing of the reinforcing bars. You got to get this aggregate around and through the reinforcing. 1/3 the depth of the slab. He gives you some rules of thumb here. Your structural engineer is not going to follow this. He will do what the American Concrete Institute and the building code says admixtures. Oh man, there is a ton of admixtures out there that makes your concrete the greatest thing since sliced bread. You got iron training agents, you got accelerators, okay, that speed up the hydration process. You got surface active agents, or surfactants. They reduce the surface tension of the mixing water in a concrete mix. Thereby, it facilitates the wetting and penetrating action of the water for aiding in the emulsifying and dispersion of other additives in the mix. Okay, let's break up that surface tension. Okay, water reducing agents, and we got coloring agents. These are pigments or dyes added to a concrete mix to alter or control its color. And I don't get all freaky about the color stuff, because color controlling colored concrete is, I mean, it is an art unto itself, not a science. It's an art. You can throw the same coloring agent in one batch of cement out of a truck and then throw it in another one, and don't be surprised if the colors are not exactly the same. So how you control that? Paint the bloody thing. All right. So here are all your different admixtures. All right. And we talked about lightweight concrete when we talked about floors and decking and roofs, right? So you got structural lightweight concrete, and you got structural lightweight, and then you have insulating concrete, and you put perlite or a foaming agent in it, and it has a unit weight less than 60 pounds per cubic foot. All right. And I've told you before, the rule of thumb for reinforced concrete is 150 pounds per cubic foot. So to me, unless you just are trying to save structural lightweight concrete, I'd go with regular structural concrete. The difference between 150 and this, not that great. But you may have to. I mean, if you've got a roof, and all right, let's see here. Where are we at? We're at 52 minutes. Why don't we do 12:2 here? We'll do the second video right here, and we'll go into the water cement ratio, and then we'll watch a small film on how to actually do a slump test. Okay. All right. So we'll see you on the next video.